get started. My name is Casper, volunteer here, and I want to introduce you to the speaker of incremental adaptation of Spark, Dask, and Ray. So if you rode here this morning with Lyft and have some complaints, they're right here. No, I'm joking, but yeah. So here we have Liu, a science tech lead of Lyft Rider app, and as well Liu Wang, who is a tech lead of Lyft machine learning. Yeah, welcome and let's get started.
Cool. Hi everyone. Can you hear me well? All right, thanks. Yeah, it's exciting to be here. Thank you all for coming. And today we're going to talk about how to incrementally adopt a distributed computing framework like Spark, Dask, or Ray. And our talk will have 3 parts. So I will walk through the first 2 parts on why we want to do incremental adoption and why there's challenges. And then Han will walk us through like how the open source library Fugue can help with that. So why do we want to do incremental adoption for distributed computing framework? For anyone working in the data industry, we know that the data today are growing extremely fast, and the algorithms are becoming more and more complex. So sometimes we find that pandas, our best friend, became a bottleneck of our work, especially on data workloads. So this is because sometimes simply because the data is too large for pandas to handle, or the algorithm is too computationally expensive for pandas to execute, and that sometimes takes an hour or more. So as a result, more and more companies and organizations today, they are trying to adopt distributed computing frameworks to build a more scalable and flexible development environment. And the question now becomes how to migrate existing codes into this distributed computing frameworks, right? Because they have different syntax. Well, if you ask ChatGPT, we can see that there are several challenges to adopt a distributed computing framework. First of all, the complexity of setup and manages this distributed computing environment may simply seem daunting for new practitioners. And second, the old application changes on the existing workload may need resource allocations. And last but most importantly, it may seem counterintuitive, but we will walk through with real examples. It's not the more we spend into the migration, the effort we spend, the more performance gain we got. Sorry. So this all calls for the need of incremental adoption of distributed computing system, and particularly, for the portion of workloads that can truly benefit from the additional resources. So for example, for training multiple machine learning models in parallel, and for some of the feature engineering steps are super expensive, and of course the data preprocessing and sampling step. And there are several critical benefits from doing so. First of all, it will reduce the all-in risk, and we will be more cost effective. And it also minimizes adoption effort to achieve the business objectives. And also we will be more flexible on the technical decisions. All right, so incremental adoption is really great, but what is preventing us from doing so today? And we will see this from a real example. So here we have a data frame that has unsorted columns, and with a large number of unique ID on the very right. And for each of the unique ID, we have multiple time series. We have 10 columns of time series. And it is a very standard way to find outliers for time series is to calculate the z-score of the time series. So assume we have this existing Python function that do the sorting and find a z-score for each time series. And now all we want to do is we want to scale this existing function out with Spark as an example. And when people are doing it, there are two very common false beliefs. The first false belief is people think zero rewrite will work. I can just do a drop-in replacement, and then I will fully leverage the distributed computing system. I don't need to rewrite my code, and the performance will be linearly scaled up. And let's see why that is not true. So using the example function without touching it at all, we try to call PySpark pandas to execute, and we can see the code simply cannot compile. And the reason is the PySpark pandas does not support for the sort interface. So then let's try to remove the sort. It still doesn't work. This time is because PySpark pandas or callers, it cannot find a unique ID we set as an index, which pandas could. So it looks like drop-in replacement cannot be 100% consistent with the original solution like pandas. And let's give it a last try. Since the pandas group by part is too complex for callers to handle, let's try to just move that out from the original function, and we rewrite using callers group by. And this time, the drop-in replacement finally works. But remember, our goal is not to have it work, but to have decent performance improvements, right? So to test the performance, we run this function on different numbers of time series, and we can see that the blue bars are PySpark pandas solution performance. I would say suboptimum, and we compare it with a alternative solution in the red color here. So with a more appropriate implementation of the method, and we can see the performance is 10 times faster. So Han will show us the details for the alternative solution in a second. I will keep it as question mark for now. So this is the first false belief that we can do zero effort and get good performance. And the second false belief on the other end is believing that I didn't get a good performance because I didn't rewrite enough amount of code. I can get the best performance by rewriting all of my codes using a native API. So is that true? Let's test it out. Using the same example, this time we rewrite the entire z-score Python function using Spark SQL. And now it has nothing to do with Python. And to make sure we are fully leveraging native Spark, this time we also run the test on the Photon environment on Databricks. And here is the result. So the yellow bars are the native Spark SQL on Photon. It is really mind-blowing that this native Spark SQL solution on Photon is not even better than the Coalesce solution. And we can also see that from the 10,000 to 100,000 series, the performance is consistently worse. And for the 1 million series case, it runs for over 10 minutes, so we simply stopped it. So while this indicates that the most native solution is not necessarily the best solution. So to summarize what we learned from the above examples, there's no zero effort migration to allow us to just have the distributed computing power, but we always need to rewrite the code to make it work. And the semantic consistency does not equivalent to the optimum performance. And lastly, fully rewriting the code doesn't guarantee the best performance. So now we have seen the importance and challenges of adopting a distributed computing framework. And next, Han will walk us through how the open source project Fugue can help.
Thank you, Jing. Hello. Thank you, Jing. Hello, everyone. So now I'm going to talk about how Fugue can help incremental adoption of the distributed frameworks. First of all, let me quickly explain what does Fugue do. So we know that Python pandas, now we have Polars, PyArrow, they are pretty popular right now. And they all work perfectly on the local Python environment. And they have their own interface. They run very well, right? But what if the data is too big or the compute is too expensive and you want to use a cluster to distribute this workload? And we can consider Spark, Dask, and Ray. Yes, we can, but the problem is the complexity will be very high. So think about that. Pick each one from left side, each one from the right-hand side. The syntax to make them work together will be totally different. And see how many different combinations you have. So the idea of Fugue is to build an abstraction layer on top of Spark, Dask, and Ray, as well as the local execution environment, so that if you just add a very thin wrapper of your existing Python pandas, Polars, PyArrow code, and then you can use the unified way to interact with different environment, to operate on different environment. And we will guarantee the optimal implementation of the code as well as the consistent behavior across different backends. That's what Fugue tries to do. Okay, so let's take a look at an example. So remember that in Jing's example, in order to make PySpark pandas work, we have to create this z_score_pd function, which operates on one partition of data. And then we can use this dropping replacement magic to work to scale this compute in a Spark cluster, right? So alternatively, if you want to use Fugue to solve this problem, it's not really bad. So this is the Fugue solution. And it will generate the same result. As you can see in Fugue, you just import transform from Fugue. And then you just do, the first parameter is you can input any data frame. Second is the method, which is z_score_pd. And then specify how you partition the data, specify what parameters you want to use, and as well as output schema. That's it. And pay attention to any data frame. Actually, that is a very special feature of Fugue, is that your execution, how this is executed, it can depend on the type of your input data frame. If it is a pandas data frame, the execution is just on pandas, single thread. It's easy for you to debug and easy for you to find the stack trace without a lot of noise from Spark, right? But if any data frame is a Spark data frame, and then the whole execution will be on the corresponding Spark cluster distributedly, and output will be the native Spark data frame. So using this syntax, you don't lose anything, but now your logic, the z_score_pd, can operate on any data frame that Fugue supports. Spark, Dask data frame and as well as array data set. Let's take a look. Let's take a further step. So remember that this was the original function, right? We had to rewrite that function to the previous function in order to make PySpark pandas happy, right? But now the question is, can we even avoid the rewrite? Can we directly distribute this function on any distributed computing cluster? So actually using Fugue is almost the same. The only difference is here, the algo now we change to calls. What does this mean? This means I only need the distributed backend to do calls partitioning for me, meaning that for each partitioning it can contain multiple UIDs of data, but for each group of data, it can only stay in one partition. With this type of like a partition spec, we're able to just use the distributed backend to do calls partitioning and then apply the Z-score GP on each of the partition. And as you can see, in this way, we totally avoid rewrite. No rewrite. You have your original logic work, and now just one single function. And this also, I need to point out, this is purely additive. So far, we didn't change anything on your existing code. Nothing, no change. Just, it's purely additive. So now let's take a look at the performance. So Jing mentioned that the red bar was like 10 times faster than the blue bar. The red bar is actually the calls partitioning solution. As you can see that we didn't add like additional complexity. I mean, it's not dropping replacement. Of course, there is a very thing wrapper, a little bit more code, but that code is purely additive. But as you can see, we get a huge performance improvement compared to the magical dropping replacement, right? Okay, so you have seen the performance and the simplicity of the solution. Now let's talk about what will be the process for incremental adoption. How can we move one step in a workflow to Spark, Dask, and Ray? Here is just something that I suggest. You don't have to follow, but I really feel this is the practical way I follow. I feel it is very, very powerful. So if, let's say, you want to scale out Z-score PD, right? The first step is to just create a small pandas sample data frame that is small enough, and just use transform to run it lightly. And in this way, you do not need to have a distributed backend. Everything is just local, okay? Because Fugue guarantees the consistency, so you know that if you change the engine or change the input, it will give you consistent results. But in this way, you can quickly iterate, right? You can iterate very quickly. It's small data, and it's local. And then if there is anything wrong, you just change and then run again. You get very quick iteration without high cost. After you have high confidence this works, the second step would be just to convert this small sample data frame to a Spark data frame. It's still small, but the second step is to test the distribution of logic, right? You don't have heavy compute, but you know that you want to make sure that this function will work on a remote, on a worker node, right? This is also a very important step, and do things iteratively. The first step is to check if the logic is correct. The second is to check if the distribution is okay. And the third step, simple, is just to replace that sample DF with the full-scale Spark DF. That's it. So if you follow this sequence, you will find your iteration speed will become much faster. Because most of your time will just spend on your local machine and just to iterate on the first step. Similarly, if you want to move this to Ray, it's also the same. You just convert the PD sample DF to Ray sample data set. It's one function call in Ray. And then to test the distribution on Ray. And after it's working, just use the full-scale Ray data set. And similarly for Dask, I didn't list it here, but it's actually the same. So to summarize, why Fugue can help incremental adoption. First of all, the core computing logic can remain untouched. You don't need to touch it. The change is purely additive. You just add one more function call. That's it. Okay, and because this is purely additive, the migration is also reversible. At every step, you add something, you don't like it, remove it, because your core computing logic is still the same. So the third is the existing unit and integration test should still work. Because remember the transform, if you just run the transform on pandas data frame, it should still give you a pandas data frame as a result. So the existing tests should still work. And also the iteration will be a lot faster because you move a lot of the heavy steps just to your local iterations. Last but not the least, the migration itself is not to tie yourself to another distributed backend, a heavy dependency. Instead, you are creating something that is scale agnostic and platform agnostic. And on the Fugue level, guarantee two things. One is the consistent behavior by switching different backends. And the second is the best possible implementation on each distributed backend to maximize the utilization of the system. Okay, so I have been talking about the Python interface, the Python thing about Fugue, right? We know that for Fugue API, we can use Pandas, Polars, Spark, Dask, and Ray as the backend interchangeably. Actually, Fugue is also very good on SQL side. We have good integration with DuckDB, BigQuery, Trino, and we are working on Snowflake integration. So now let's talk about incremental SQL development. So here I want to have a pause and I want to have a survey like how many people here are also SQL users? Wow, a lot, a lot. Great. Awesome. Yeah, so let's take an example. So this is TPC-DS. It's a pretty popular benchmark query set. And we take number 78. It's a complex query. It's very long. You don't really need to read through this query. But think about that. In your real work, how many people have ever written such kind of long SQL using CTE statement with statement, right? It's a lot of code, right? And so let me just segregate this code. You will see that it has 4 parts. In the with statement, we have A, B, C, 3 subqueries. And the D is the final query that will consume A, B, and C. Okay, so this is the DAG. Now let's see why SQL development is so hard. Why developing such a big query is so hard. Okay, the first question, how do you iterate on each individual step? Let's say you have already developed step A, B, and C. Now you want to iterate on D. What are you going to do? Like for every change you make, you probably just rerun everything from A, B, C, and D, and the current version of D on the big data, very big data, right? It wastes a lot of time. And even for a small change, you have to rerun everything. That iteration is too slow, right? And the second thing, I believe there are Spark SQL users here. And I think you probably know more about this pen. But of course, for BigQuery and for other SQL, you also have this problem is if the SQL is slow, like this BigQuery is slow, like where is the problem? How can you find out that? So notice that Spark SQL has very good optimization logic, very good, very smart. But the problem is, the consequence is the execution plan should be very different from your logical plan and from your semantic expression. So in a lot of cases, you have Spark UI. You have the very nice stack of Spark UI, but you still cannot point out, okay, where exactly is the problem? It's stuck, but what the hell is that? I don't know. I still don't know. So it's very difficult for such a complex query, to debug the performance issue in such a complex query. And the last but not the least, how do you test the SQL? So I see a lot of SQL users. How many of you are really testing your SQL using unit test, integration test, and in production? How many of you? You raise your hand. Nobody. Right. SQL is really difficult to test. I know, I understand. Yeah, this is the common pain point. Okay, so first of all, let's see how Fugue can help to break up this large SQL. You can see that for this part, this is the first part. What we can do, assuming that you are iterating that on a Jupyter notebook, you can use this FSQL. You can use this as FSQL magic, and you can use Spark as the backend. Assuming the original query is running on Spark. If it is original query is running on BigQuery, you can just change the Spark to BQ. Will also work. And the important thing here is, what I do is, I'm using Fugue SQL. So what is Fugue SQL? Fugue SQL is a superset of standard SQL, adding some necessary syntax to make SQL more capable to express your end-to-end work logic. So we have some additional syntax. Here is, we say we want to sample the result, 1%, take 1% result, and then I want to yield that as a local data frame that exists on my Jupyter notebook. So after this execution, your Jupyter notebook will have a variable called WS, that is a local data frame that you can consume in the next step. Okay, so this is to sample a very small portion of data to local for the next iteration. Okay, another way, if you think, I don't want to sample down data, and I don't want to collect anything onto my machine. Okay, what you can do is you can yield file as, and this yield file will make this whole thing totally distributed. You distributedly run the SQL, and then distributedly write the result to a temporary file on the cloud so that you have the CS as the reference. You can still consume it on your Jupyter notebook. Both steps, what's the purpose of the steps? Is to cache. Right? If you cache this step, no matter how long it takes, 10 minutes, 20 minutes, and in your iteration on other parts, you will never need to rerun this. You will never need to rerun this. So the iteration becomes, isolated. You don't have to, every time you don't have to start from the very beginning. Right? Okay, so now let's move to the last step. Assuming that we choose the first, which is we want to sample down the data, and just to cache them as like a sample local data frame on Jupyter. And in the end, we want to iterate on step D. This is how we do that. As you can see, something to notice is now I'm not even using Spark. Now I'm using DuckDB to iterate on the last portion of the SQL statement. Why? Because now I have SSWSCS as the local data frame. If it is there a local data frame, I just use DuckDB as the local execution engine to iterate on the SQL. So that will significantly speed up your iteration, and as well as the print statement and some other syntax that can help you further improve your iteration experience and speed. Okay, after everything is working, now I will just combine everything together. Do I need to put them back into with statement? Actually, no. This is another feature of Fugue. In Fugue, you can linearly combine your statements using this simple assignment syntax. On the back end, I can tell you on the back end, it will translate this to with statement, to the CTE statement. But you don't have to care, and there is no performance penalty during execution. We focus on a better semantic, a syntax, and we think CTE is not good. So we make this possible. So you can linearly combine your SQL statement. So in the real experience, you literally only need to copy paste the code from different cells into one cell, and that will work. You don't have to add additional syntax to make it work. Okay, so if we take a look at the whole process, we have A, B, C, D, right? Now what Fugue helps is now you can individually develop on each of the steps. We are totally isolated. You iterate on each of them. And more importantly, because for B and C, you bring them to local, then some part of the DAG, the development, can be totally local. You don't even need a distributed system to develop that expensive SQL. And after development, you just change the backend from DuckDB to Spark. It will work. And the last thing I want to talk about is testing SQL. Look at this, Hive SQL, all right? you will have 100 excuses that not to test this. This is a Hive. How can I do unit tests? How can I do like integration test? Let me show you how we can do unit test on this table. So this is how you do it. First of all, we mark this table with a pandas data frame, run the SQL using fSQL, and then we just change the backend to DuckDB. Now this part becomes totally unit testable. As long as you have the input data frame, and you can also, the output of this will be also a pandas data frame. So you can assert on output pandas data frame. So we turn this into a unit testable problem. Okay, so key takeaways. If we have this chart, and the y-axis is the business scan, and the axis is the adoption effort of a distributed system, I think actually it is a curve. It is a curve that will go down in the end, right? So it doesn't mean the more effort you will have more business gain. No, you will not only have diminishing gain, you will have reduced gain. And if you just blindly start the full adoption, it's very likely you will fall on the right-hand side of the chart where you reduce the gain. You waste a lot of resources, time, money, right? Instead, what we want to do is we want to incrementally adopt the system until you see the diminishing return. You can stop. You don't always have to find the optimal point. Not necessary, because I think sometimes just keep it like in a reasonable, keep your effort in a reasonable size is also very important. So in this way, actually, you can closely monitor like the value of your effort. And this is difficult, I understand, but I think this is how Fugue can help you to make this process easier and smoother. Thank you.
Any questions?
Yes.
As a library developer, can I take a dependency on Fugue and have it so my users can choose which backend to use, even if I don't have to test all the different possible backends?
Yes. It is so it requires a lot of effort, but I believe we have done a great job on that. Yeah.
Still a question here? You still have a question? Oh, you had.
Yeah, I'm curious on the SQL workflow, since we are switching backends to that DuckDB. Obviously, SQL backends have slightly different syntax sometimes. I'm wondering how you handle that.
So we can you can choose like what kind of syntax. So by default, for Fugue, by default, you are always using Spark syntax. And when you run as DuckDB, we will transpile this to DuckDB SQL and run. Yeah. So you can also change the default syntax to DuckDB, and then you just use the most native DuckDB syntax. Yeah.
This is very cool.
Thank you.
I'm curious about the first part where you had the transform function.
Sure.
In the types that you talked about, the input data frame could be any of the supported platforms.
Yeah.
But the function that you had was written using pandas.
No.
No?
Not necessarily. So here is another thing I didn't have time to explain. For the function that Fugue can support, as long as you have the type annotation, we almost can do the auto conversion. So what we have, you can change the pandas pd.dataframe to polis.dataframe and still keep the output as pandas dataframe. It still works. So what we do is we can recognize your type annotation and to do the data conversion for you. So when you write this function, when this function is run on worker, when you get the data is already converted to the thing that you annotated on your function.
Okay, so you will do the partitioning and then on the worker convert
we do
to
the
the
data
right thing.
conversion. The data conversion is actually a big deal because now you have super flexibility. So what I commonly do is, for example, the input is a list of dict. Here, I give like a list of dict, right? And the output can be an iterable pandas data frame, or a list of polars data frame, or things like that. So you have a lot of flexibility. So this is another design philosophy of Fugue is we adapt to you instead of I ask you to adapt to me. We have very flexible interface. We almost, at a certain period of time, we call it interfaceless because we really want to be very adaptive to your logic. Yeah.
I'll just ask a quick follow-up on that. Do you use Arrow under the hood, or do you actually?
We try to use Arrow as much as we can. For example, for Fugue, the typing system is all Arrow. It's not pandas. Yeah.
Any further questions? Okay, if not, thanks to speak. Oh, yeah.
Mic and everything. Okay, it works. Okay, I'm curious. The transform function, does that transform our, in this case, pandas code into PySpark code? Or
no, it's actually if you are using PySpark.
Yeah.
And if the input is pandas data frame,
yeah.
we will try to use pandas UDF. Mapping pandas, applying pandas. So actually, we use those functions as much as we can. But if you turn off pandas UDF, we will use map partitions to do those kind of thing.
Okay.
Yeah. So in the backend, we try to use the best available methods to process. For example, if your input is arrow, and your output and if you don't do group by, and in the latest Python 3.3, we now have mapping arrow. So if we recognize your input is arrow, we directly use mapping arrow to process this function.
Okay.
We always try to use the most efficient way to process your logic.
I guess I was just worried that because of this transform becomes an abstraction, if the resulting code is either slow or doesn't work, how do you then debug the transformed operations?
Function? Yeah. So as I said, you should iterate locally as much as you can. If there is any performance issue, I hope that you can really find that out in your local system.
Okay.
But it's not guaranteed. I mean, in a distributed system, there can be 100 places to have problems. Like, for example, you in a machine learning code, you forget to set the thread to like a small number, and so you generate a lot of attention. Those kind of things can happen. Yeah. So you still need the certain experience for certain cases to debug. Yeah. We cannot cover 100% case, but we try to cover as much as we can.
All right.
Yeah.
Thanks.
You're welcome.
Any more questions? If not, we thank the speakers again. Thank you very much.
Thank you.